Michael Smith is a British-born Canadian biochemist who has made significant impacts in the field of biochemistry. He was intrigued by chemistry from a very young age and thus began his studies in an honours chemistry program at the University of Manchester, where he later obtained his PhD. Throughout his professional career, he worked on a great variety of projects, but his most significant contribution, for which he won the Nobel Prize in 1993, is in the development of site-directed mutagenesis. So what even is site-directed mutagenesis? This is a technique that allows scientists to deliberately change a particular nucleotide sequence. In vitro, STM can be performed with or without polymerase chain reaction, using a 20 to 30 base long primer that is complementary to the target gene, but include a desired mismatch. The PCR-mediated technique tends to be favorable as it produces many strands. A variety of different PCR-mediated approaches have been developed. However, the most common one involves using two complementary primers. A plasmid that contains an antibiotic-resistant gene and was grown in an E. coli dam methylated is used as a template DNA and is cut with DPNI restriction enzyme. The plasmid is then amplified with PCR. The nitration of the hydrogen bonds occurs at 95 degrees Celsius. The primers are then annealed to the sequence of interest at 55 degrees Celsius and extended by DNA polymerase at 72 degrees Celsius. The PCR product is then transformed into E. coli using either heat shock or electroporation. Both methods make the plasma membrane permeable and allow DNA to enter. After transformation, the scientists can verify the success of the procedure and isolate mutated colonies. STM is quite a complicated method that opens doors for examining mechanisms of genetic diseases and genome modification. This raises the question of how Michael Smith came up with this technique in the first place. His original hypothesis for STM began when he met Clyde Hutchinson III, who mutated a virus using bacteriophage and restriction enzyme and had the virus replicate inside the bacteria. Inspired by this, Smith hypothesized that one can achieve STM by altering the sequence of the DNA fragment using a mutant primer and inserting the mutated fragment into a host organism. Smith and Hutchinson used a 12-base long primer with a singlet nucleotide mismatch in the center that changed a TGG codon to a TAG codon, thus changing a tryptophan to a stop codon. They further used a 5x174 DNA template in E. coli DNA polymerase 1, along with subticillin to inactivate the 5' exonuclease activity of the polymerase to be able to construct a closed circular double-stranded DNA. The development of this technique was very significant in biochemistry and research. For instance, using STM, scientists have been able to understand the relation of plaque formation and pathophysiology of Alzheimer's disease, along with studying gene therapy approaches for sickle cell anemia, hemophilia, and cystic fibrosis.